Hello everyone. In the previous class, we have discussed about transistor switching, in which we have discussed how the transistor switch from one region to another region, and we have seen the different regions: normal active region, saturation region, cutoff region, and inverted region. And also, we have discussed the cutoff region and the saturation region in which the transistor mainly switches. So in today's class we are going to discuss about the switching cycle. So the figure shows the switching effects in a common emitter transistor circuit. The figure A shows the circuit diagram. So it is a common emitter transistor circuit because the emitter is common between the two sides. That's why it is a common emitter transistor circuit. It is called as. And the second figure shows the approximation hole distribution in the base during the switching from cutoff to saturation. Here there are four terms used: T0, T1, T2 and TS. So T0 represents the cutoff region when both the emitter junction and collector junction are in reverse bias. This transistor is in cutoff region, so that T0, the where the operating point lies, so that is shown here. Where the approximate hole distribution in the base region from the switching from cutoff to the saturation, from this region to the saturation region, how it takes place. Then T1 shows the normal active region, TS shows the beginning of the saturation, and finally T2 shows the final saturated state. So these are the terms that are used: T0, T1, TS and T2. Cutoff region, normal active region, then beginning of the saturation and final saturated state. So this beginning and final saturated state we have discussed previously. The same thing is shown here with complete all the different regions. So the various mechanisms of switching cycle are shown here. So if the device is originally in the cutoff condition, that means if the device or a transistor where emitter junction as well as collector junction, if it is reverse bias, then it will be in a cutoff region. Here a step increase of a base current to IB causes the whole distribution to increase approximately as illustrated in the figure B, or as shown in the figure B. So here at the time Ts, observe the figure B, at the time Ts the device enters saturation. Ts represents the saturation time. So device enters into the saturation and the whole distribution reaches its final state at T2. So T2 is the final state of the whole distribution, beyond which there is no further increase in the whole distribution. As the stored charge in the base QB increases, as we know that Q is represented for charge, so the stored charge in the base, that is QB, B stands for suffix B stands for base here. So QB increases, there is an increase in the collector current IC. So the collector current does not increase beyond its value at the beginning of the saturation Ts. So we can approximate this saturated collector current as IC equal to ECC by RL. Observe the figure A, where ECC is the value of the collector circuit battery. ECC that represents the battery in figure A, and also the RL is the load resistor. So this is the figure C, which shows the base current, stored charge and collector current. The first one is the base current, the second one is the stored charge, and the third one is the collector current during turn on and turn off transients. There are current which turns on and turns off. So both are shown here. So the base current IB, stored charge QB, and the collector current IC are shown here in the figure. So referring to this figure, there is an essentially exponential increase in the collector current. You can observe from the 0 towards Ts, there is an exponential increase in the collector current, while QB rises to its value Qs at Ts. So observe figure number B and second figure and the third figure in the figure C. So here there is an exponential increase in the collector current, while QB rises to its value Qs at time Ts, that is at the beginning of the saturation current Ts. So this rise time serves as one of the limitations of the transistor in a switching application. So this is a drawback, or this is a limitation. Similar to this one, when the base current is switched negative, observe the first figure. In the first half, the base current is in a positive half cycle. In the second half cycle, the base current is negative. So when the base current is switched negative, the stored charge must be withdrawn from the base before cutoff is reached. So while QB is larger than the QS, so see the figure carefully. While QB is larger than QS, the collector current remains at the value IC, which is fixed by the battery and the resistor. Therefore, there is a storage delay time, TSD. So the TSD is marked in the second figure. Just observe carefully, TSD. TSD stands for storage delay time. After the base current is switched and before IC begins to fall towards 0. After the stored charge is reduced below QS, IC drops exponentially. So observe the third figure, in which again the collector current drops exponentially. So after the stored charge is reduced below QS, what happens to the collector current? That is, IC drops exponentially with the characteristic fall time. Once the stored charge is withdrawn, the base current cannot be maintained any longer at its large negative value and must decay to the small cutoff value. So observe the IB. So once the stored charge is withdrawn, what happens to the base current? Base current cannot be maintained any longer at its large negative value. So it is reduced and must decay to the small cutoff value. So this is what the switching cycle. Thank you for watching the video.